Thanks for having me. It's been a lot of fun. I'm very out of my So yeah, I'm going to talk about some work that I did in grad school with Smith, a few hours south of here. So, you know, if you want to kind of do some experiment comparing, trying to reconcile gravity and quantum mechanics, you'd say, well, you want to have control over whatever gravity is, or gravitational fields are impacting the particles, and you also want to have strong control over the actual quantum system. But gravity is actually like a quite difficult thing to experimentally control, right? Like we're on Earth, which has a very large gravitational field, but you say actually, well, I want to study probably something with a much stronger gravitational field, maybe a black hole, and that's something that is not feasible in the near term, let's say. So you can kind of try to take inspiration moving from like a sort of holographic picture, right? Like maybe I can create some sort of quantum system that is dual to some sort of gravity theory and use kind of some extrapolate dictionary from my quantum system to learn about the gravitational system and maybe have some sort of comparison between clear theory and experiment. So this would sort of be one kind of protocol you can use to kind of experiment. And you know, this holographic correspondence is, it's I think the most cited physics paper in the last 50 years or something. You can ask, well, how many of these are experimental, you know, realizations? I kind of went through like a random sampling of like 300 basically until I found an experimental proposal. But you know, graph in log scale. Yeah, but the reason is that, you know, controlling quantum systems is also a really hard problem, right? Because I want to have an isolated quantum system where I can see what's happening inside, but I need to make sure that it's isolated on a quantum mechanical level from all of its surroundings, right? So, you know, if I have my system, we have, you know, photons all around us. There's, you know, Wi-Fi signals, whatever's coming from your cell phone. All these things can actually, you know, interfere with some experiment. So there has been really remarkable work in controlling quantum systems over the last 50 years, and there's a number of sort of different platforms that people use. So, and I should say, with this kind of quantum control, there's a lot of, you know, exciting applications. So there's this quantum simulation idea where we can engineer some quantum system and kind of learn about the physics. But you can try to imagine preparing entangled states that are now leverage quantum correlations to be more sensitive to sort of physical phenomena. And you know, maybe if you really like prime numbers, there's something in quantum computation. But there's been a number of really remarkable results and improvements in a variety of different quantum platforms. Over the last 50 years or so. So when you see something coming from Google, for example, they're using arrays of superconducting qubits that are all connected, where sort of quantum degree of freedom is a single microwave photon. There's also been developments in trapping single ions in chains, and you know, coupling motional degrees of freedom. These ions can be trapped in their motional ground state, and for coupling single motional quanta between ions. And the platform I'm going to talk about today is neutral atoms. So instead of ions, these are atoms as sort of God intended, electrically balanced. And this has sort of some nice properties with respect to these two other systems. The first is that it's very sort of massively scalable. You can trap single atoms in a single tightly focused laser beam, and this has been demonstrated to creating arrays of more than 6,000 individually trapped or imaged atoms. And so, you know, basically at sort of a linear cost in money and laser power, you get the sort of exponential scaling over time. And you know, as this picture sort of demonstrates, you can actually image individual atoms in 2 dimensions or 3 dimensions, and kind of each local beam kind of address each local beam. But the tricky thing, as the name kind of suggests, is how do you kind of make neutral atoms interact? How do you get them to, and unique?
Okay. So in this case, you said you can also have 3D.
Yeah.
Because I think that's a problem with ion trapping.
Yeah, so ion traps typically are limited to 2 dimensions. There are some ion traps that will do things ion traps are limited to 1 dimension. There are some experiments that put them in 2 dimensions where they're actually like sort of always spinning, which makes it very hard to do like this kind of individual testing. Yeah, you can put things in, because basically if the ion trapped in an electromagnetic field, if you can't have a conservative potential with just static electric fields, so they actually have an oscillating electric field, and so it's easier to make these traps in 1 dimension and not more. With atoms, you can use lasers to trap them. So basically, as long as you can engineer like a laser intensity profile and sort of whatever shape you want, you can trap the atoms in that dimension. The tricky thing with 3 dimensions is actually like you can only really image a 2-dimensional plane. So if you want to image in 3 dimensions, you have to sort of do sequential images of different planes and then hope that your atoms in each plane are not interfering. So that's typically these experiments are limited. Yeah, so the tricky thing is how do we generate interactions, and we need interactions so that we can have some sort of entanglement, which is sort of defining quantum many-body. So there's some sort of very impressive work in programming lattice potentials using lasers and allowing atoms to hop between different sites of the lattice, and they can sort of hop, 2 atoms can hop into the same site and then hop out and exchange information through this sort of direct contact interaction. There's also been a lot of work with Rydberg atoms. So here the idea is I excite my atom to a very high end, like a highly excited state. And so now the electron, instead of having sort of like a very small radius with respect to the nucleus, has a sort of effective radius that's order microns, which is basically the distance at which you can sort of keep 2 atoms trapped. So you can use this sort of large dipole moment that you're providing by exciting the atom to kind of decouple the spin degree of freedom and motion. And so both of these have been used with to study condensed matter systems as well as quantum computation platforms. So in particular with the lattice, these kind of mimic condensed matter systems where atoms hopping in the lattice act in very much the same way as electrons hopping in a crystal. And so they can provide kind of microscopic visualization of phenomena that people have seen in sort of traditional condensed matter samples. And this is sort of one example of looking at kinetic magnetism. Yeah.
In the Rydberg system, are there any experimental challenges in the fact that you're very close to ionization and all of the divide levels are very close to it?
Yes. So people have to, do some amount of work to make sure that the electric fields are relatively stable. So for example, these experiments happen in a glass cell. Not technically, maybe it's an interesting thing. You can have charge buildup on the glass cell, which will act as an electric field, which can impact your physics. So what we'll do is shine a UV laser onto the glass cell, once every second or so, and that will kind of de-ionize the glass cell. So you have to always be careful about whatever magnetic fields.
I meant more so that you had a bunch of these highly excited things, and they could accidentally hop like
Oh, okay, yeah. So the spacing. So let's say we work at like n equals like 75 or something. So the spacing between adjacent river levels is still going to be like 75 gigahertz. So for comparison, like a typical like microwave that you eat food in is going to work at like 3 gigahertz. So it's still actually quite a large energy. Yeah, and then these Ripper interactions have been used to sort of do I'd say the first, some of the first demonstrations of fault tolerant quantum computing, and have been used to do really generate entanglement and actually serve as some of the world's most precise clocks. Okay, but both of these interaction mechanisms are sort of spatially localized, right? And so you can ask, well, what if I want to generate a state with some very long range stopping entanglement? Well, with these sort of local interactions, I need to wait maybe an extensive amount of time with my system size because there are some sort of effective with sort of these local interactions. So I'm going to talk about sort of an alternative approach today, where we start with a very top-down setting where you entangle a whole bunch of atoms in a very all-to-all kind of way, and then prune the connections down to generate kind of the structures you're interested in. And the way we're going to do this is by coupling atoms to a single mode of an optical resonance. So, in particular, cavities have this kind of Hamiltonian, where the key point is if you look on the sum, it's not over neighbors, it's over all possible pairs of atoms. So there's interaction between every possible pair of atoms. And you can turn on interactions just by sending light into the cavity. This has been used for a variety of different kinds of state engineering and quantum simulation protocols. And you can use the light leaking out to effect measurement. I'm not going to talk about that very much, but so Dan Stanford Kern at Berkeley here, for example, has an experiment that uses a sort of similar setup for looking at measurement. And this has been used to generate entangled states with sort of hundreds of thousands of atoms. But what's sort of missing is control over the entanglement and the ability to detect any kind of structure. And there's been a lot of work in I'd say the last 10 years in this direction from a number of different groups kind of, so today I'm going to talk about sort of how we can combine these non-local interactions with just sort of single particle operations to really control the structure of entanglement. We can use that to make Hamiltonians that have sort of programmable geometry, so we're no longer limited to being this two-dimensional plane or three-dimensional plane. It's just something you ask for. And then we'll talk a little bit about some sort of gravity-inspired models. Okay, but first let's talk about generating entanglement. And in particular, how do we combine all-to-all interactions with these sort of single-particle operations for something that's sort of more programmable? Just to take a step back, this is a picture of the experiment I worked on. This is just one of 2 optics tables. But if you zoom in a little bit, sort of towards the center, there's a vacuum chamber. And if you look inside the vacuum chamber, there's 2 mirrors spaced 5 centimeters. And this forms an optical pattern. Now, schematically, what's going on is these 2 mirrors. You can form a lattice, a standing wave, which will trap atoms or ensembles of atoms, and we can put a lens underneath to image the state of the atoms. Now, we're using rubidium atoms. Rubidium with 1 valence electron, which makes it kind of easy to address by just manipulating this 1 electronic state. But for the purposes of this talk, we're going to encode spin information in this sort of bottom f equals 1 sort of hyperfine manifold, really you can just think of, we have these spins that are Q trips, really, and we're going to have a few thousand of them in each kind of spatially separated ensemble.
So can you explain again what their Q traits?
So there's just 3 levels, and we can image each of the 3 levels in this f equals 1. So yeah, we image each of the 3 levels. That gives you a population. So when you send light into the cavity, well, we prepare our ensembles in some sort of specific state. As you send light in, one. So as you send light into the cavity, you can excite a single atom, which will then emit a photon back into the cavity, which will bounce around and then get absorbed by some other atom. So, every interaction between the photon and the atom is spatially local, but if we remove kind of the action of the photons, it's a non-local interaction between 2 atoms. So in particular, we're going to prepare all our atoms in this 0 state, this middle state. And when we drive interactions with some pair of atoms, what you can have is this sort of pair creation process whereby we turn 2 0 atoms into a pair of +1 and -1 atoms. But generically, I don't know which one is +1, which one's -1. So I've basically turned, some pair of atoms that are in the same state into this sort of bell-like state. So this Hamiltonian is kind of a XY, it's this spin exchange Hamiltonian where one atom or one ensemble gets a spin excitation from some other ensemble. Now, we have these ensembles, and I said, we create some sort of bell pair, but how do you actually measure any kind of entanglement generation, right? So if I have, 10,000 atoms, each one shown by a green dot, and I'm looking, really the experimental task is to look for the 2 red dots that are entangled kind of each dot. So hopefully you found it. Okay. So the way we do this really is to say, well, entanglement means there's some sort of correlation in the quantum fluctuation, right? So if I have 2 observables that are conjugate, say x and p, if I don't have any entanglement, Heisenberg's uncertainty principle tells me that, well, any basis I measure in is going to have an uncertainty that's 1 over square root of n, where n is kind of the number of atoms, right? Because they're all independent, so there's n independent. Now, if I have some sort of correlation, then these measurements can become dependent, right? And so there's a particular basis that I can measure in, right, where I'll see an increased sensitivity that can scale as up to 1 over n, right? Now, you can't ever, violate the uncertainty principle, so you're sort of increasing sensitivity along one axis at the expense of decreased sensitivity on another axis. Now, notably, this kind of squeezing for entanglement generation is used in photons, in particular with LIGO. I think it increased their sort of black hole detection rate by maybe an order of magnitude. But we're going to do this with these atomic spins. So we just turn on the interactions. You can basically measure along one basis and look at the variance and sort of rotate your state and keep it. So
Spin basis?
Yeah. So x and p are just, it's the spin 1 operators. So yeah. Yeah. So you can sort of carefully calibrate your imaging so you know what the sort of projection going limit of say 1,000 atoms is, and then you can just measure the variance as a function of this angle. And you can see, you sort of, if you generate the squeeze state, we have, which we do, we have variance that's smaller than the standard quantum limit, and sort of 90 degrees away, conjugate quadrature with increased variance and decreased sensitivity. Now, squeeze states are kind of fundamentally entangled, but we can ask a little bit about what's the spatial structure of entanglement. In particular, if I want to know the left and the right clouds are entangled, we can construct a witness, which basically is the product of two things. One, if I want entanglement, I need things to be quantum, and I also need them to be correlated. So we need the variance of sum. The sum, let's say, in one basis to be reasonably small, otherwise we're just making a classical amplifier. And then you need a correlation, which means that the variance between the difference of these two sides has to be small. So normalized basically appropriately, this says that I need the variance of the sum and difference be less than 1. We can just look at the same measurements, and instead of adding this width and looking at the variance, you can look at the difference. And you can see that it really doesn't change as a function of the information. Now, so by this witness, we can say really there's some entanglement between the left and right sides. But I think the actual question is, once we say, well, how do you control the structure? Well, this difference actually didn't change. Like if we hadn't turned the light on, the interactions on, you'd also expect to just see this kind of coherent state. So the difference is really not coupling. This difference collective mode is not coupling. And so what you can do then is use this kind of ability of local control. So use single laser beams to take these 4 ensembles. If I shine light on just 2 of them, I can perform a local rotation that will map, say, this symmetric mode onto an anti-symmetric mode. And this gives you some ability to control the structure. So let's look at that in a very concrete way. So what you can do is perform our initial squeezing operation, perform this local rotation. That's going to map the sum into the difference, but it's also going to map the difference back to the sum. So we sort of swapped these 2 squeezed modes. We can then do some sort of global rotation, right? Now the sum is, rotationally symmetric. It's not going to change, but the difference has now been squeezed in orthogonal quadrature. But if you apply the squeezing again, well, it's not going to change the difference, which we established, but it is going to change the sum. So now you have squeezing kind of in 2 orthogonal quadratures in the sum and the difference. If we think about this sort of entanglement criteria, it actually makes both this x left plus x right and the p left minus p right both smaller than 1. So in some sense, this is a kind of the maximally entangled state. So this state is an example of the kind of Einstein-Perelsky-Rosen experiment, but that's a little bit of an aside. So let me just move on to say, like, we can use this to make sort of even more structured states. In particular, we can make a set of states called graph states, which act as a resource for kind of universal quantum computation or for sort of multi-parameter testing. So these states are defined by a set of squeezed modes given by some graph with adjacency matrix K. And so this says basically if I pick some site I in one basis and the P basis, it should be strongly correlated with its neighbors in the sort of conjugate basis. So if we want to make this square cluster state, we can just go through the set of modes. And you can write down the set of 4 sort of modes that you want to squeeze, and you say, okay, well, this is now a little more tricky because the cavity's coupling to all the sites at once, but I need to sort of address 3 at a time. But what you can do is say, well, we know that these symmetric and anti-symmetric, well, I guess what you should say is, well, if you see a matrix and you study quantum mechanics, the natural inclination should be, well, can I diagonalize this? And if you do, basically you can rewrite the sort of set of modes that you squeeze in a very in a way that's the same basically for all sort of collected modes. So for this particular, generically I have some eigenvectors v and some eigenvalues d, and the eigenvalues will specify kind of the basis along which I need to squeeze, and the eigenvectors will specify what the specific modes I need to squeeze. So for this example, these modes all actually look like these combinations of up and down, which are very easily performed with just the local dictation. So we can just squeeze these four modes in sort of four different bases. Well, you know, this isn't obviously a square cluster state, but we can kind of say, well, what's the actual set of correlations that we measure to sort of invert this transformation? And you can see that the sort of correlations between different ensembles and different bases match very exactly with the kind of expected basis. So that's kind of the toolkit of control. I'm going to quickly talk about how you can use this and really extend this in much larger systems. So in particular, we're going to now move to ensembles, maybe 18 ensembles, and we've done some experiments with up to 40. But the idea is we're going to take this sort of protocol, and instead of having a single J coupling all possible ensembles, we're going to program in specific J algorithms. And in particular, well, we have this pair creation process. If we want to just see what's going on, we can look at what's the correlation between +1 atoms and -1 atoms on two different sites. So if you just turn on the interactions, you have this all-to-all correlation that gives you this sort of all-to-all, this all-to-all correlation matrix. So kind of boring in some sense maybe. But we can ask, well, you know, what kind of modes can we couple to? So if we want some sort of translation invariant Hamiltonian, the eigenmodes are going to be momentum modes. So if you apply a magnetic field gradient, that's going to switch you slowly between different momentum modes, different kind of spin waves. Okay. And so now if I look at the interaction between any two pairs of ensembles, they're going to always cancel out. And in particular, so if we just do this experiment, turn on the interactions with magnetic field gradient, now we only have interactions happening on specific sites, because everything else has averaged out to cancel. And now the question is, well, how do you reconnect sites at some specific distance to really program in specific modes? And so we have this gradient, we have these rotations, but you notice the way I've drawn this, at specific times, different sites will come back in phase. So if we only kind of turn on the interaction at times when some specific distance is back in phase, then you can reintroduce coupling for the specific distance. Right? Okay. So let's say we want some interaction at distance 10. There's kind of a nice energy conservation framework to look at this, where if we have some gradient, there's some different splitting in the different future based on the strength of the magnetic field. So there's an energy cost to having this kind of pair creation process. What we can do is modulate the light intensity at some appropriate frequency. We can also view this as adding in photons of an energy, slightly different energy, that now reconnects this pair creation process. So if we just do this experiment with the magnetic field gradient and modulating the intensity of the drive, then you can sort of see we've reintroduced couplings at some specific distance. And now, if you have these interactions, you can tune the frequency and tune the distance at which you have specific interaction. And there's really pretty good spectral resolution here if you modulate or send in two tones that are sort of at non-integer multiples of the spacing you've chosen. You don't see any correlation. So really the set of frequencies we're sending into the cavity is specifying the set of interactions and distance in the cavity. So you can start to play games with this. What if I send in two frequencies, one for nearest neighbors and one for the sort of n-1 distance? Well, that's going to make a ring where I have, now a system which is the 1D array of atoms interacting as if they Okay, so we have these sort of correlations when we do this experiment.
Sorry, I got some.
And we can basically ask, well, what's the kind of optimal embedding? Like, what's the effective geometry in which gives rise to these correlations? And you can sort of draw in every edge and kind of color them based on the correlation strength, and sort of get a black box way of extracting what's the effective geometry based on some set of parameters. Now, you can combine this in sort of more complicated ways. So, for example, say you wanted to make this cylinder with interactions that are now changing signs, so some weird combination of ferromagnetic and anti-ferromagnetic. You can send in two frequencies with different now phase, so just a slightly more complicated waveform, slightly more complicated correlation, but sort of a slightly more complicated effective geometry. And this is really, just type in some numbers on the computer and wait like an hour and you get, whatever set of correlations you're looking for. We can do this in a very, black box kind of way. So in particular, you can even have something interacting on like a Mobius strip, even though, these atoms are just in some array in Okay. And in particular, once you have these controls, there's
you said you have to wait an hour. You have to worry about the frequency clearing.
so it's just to get statistics. So each experimental takes about like a second, and of that second, the actual physics is happening on like a millisecond. But you have like really programmable control. Maybe you can do some sort of more exotic things. That's what we'll just finish up with. So that's sort of motivated with this idea of, well, like, can we create some sort of quantum state that's dual to some sort of gravitational theory? And then sort of an associated question is, well, maybe we have this control to make some state. How do we know that it's actually, some sort of gravitational rule? Now, we also have discrete ensembles, right, and not something continuous. So it sort of took inspiration from work from Steve Webster and Matt Heidemann, for mapping, sort of conventional continuous ADS-CFT onto the p-adic numbers, which gives you a sort of effective mapping from this continuous bulk onto a tree, and sort of a discretized boundary mapping will leaves this tree. But the real question, I guess, for me in the lab is, well, what's the Hamiltonian that I have to program in? And so from the tree, Monica and Steve and a couple of other collaborators came up with some ideas that kind of tune between a sort of tree-like geometry and a sort of spatially local. And in particular, you have this kind of two-adic inspired spin model, which has interactions only at distances that are power 2, with a strength, a sort of non-locality parameter s. So in particular, if I have S is 1, then I have very strongly non-local interactions, so that's going to correspond to a tree. And if I have S is minus 1, that's going to correspond to sort of very strongly local interactions. We'll have something more akin to sort of anonymous bit tree. And there's sort of numerical evidence. Numerical evidence that S equals 0, where I sort of tune between this Hamiltonian is a fast scrambler. Yeah. Great. So we can just program in, for example. So this is all numerics. But this was, yeah, so there's some, like, you can see, I guess, as you tune the S parameter, the sort of growth, the entanglement is like some sort of baseline, grows much faster. And, yeah, I mean, also this good growth. Although, I mean, I guess generically on this box graph, maybe use that sort of experiment I have. So this is sort of effectively like a yeah. So if we program in this kind of S equals 1 case, this very non-local case, we have some correlation. So some correlation matrix that looks like this. You can kind of see the stronger non-local coupling, but I would say this isn't maybe like the natural way to look at this. So we can sort of go back to our black box and say, well, what's the kind of optimal embedding of locations in some Euclidean space? Right. But then if I want to back out the bulk, I'd say, well, really, I want to do some sort of RG flow from the boundary in. And we can do that basically by coarse graining different sites and saying, well, the two sort of strongest correlated sites, let's just draw a connection between the two and treat them now as one site, and kind of repeat this process until we have a path from any site to any other site. Sort of the most maybe like night-night approach. Okay. So you can just do this, and you'll see that this tree kind of naturally shows up. And in particular, you can say, well, what if we just take this correlation matrix and map the kind of tree structure from the spin chain? That's this monomap, which is just the sort of reverse binary order. So like 0 goes to 0, 4, which is like 1, 0, 0, 0, 0, 1. And we can just map the whole correlation matrix in this way. And the sort of there's sort of this block structure that you can start to see. Sort of captures maybe the kind of effective locality, which is given by this kind of tree structure. And you can sort of ask, well, what if we do this in the sort of local case? Well, sort of immediately you connect everything into this ring. There's not really a notion in the same way of something like on a now, you can say, well, let's be like a little more concrete about this. So let's say we take our set of 16 sites and we divide it in half and look at the correlation between the left and the right as a function of the exponent. So in this blue case where I've divided things locally, you can see that I sort of captured the bulk of the correlation in the system because the correlation between the two sides is weak. Right. Okay. Okay. So yeah. So the correlation between the two paths is weak in this kind of local case because you effectively captured all of the whatever effective entanglement by just combining all the locally connected And we can ask, well, how does that look in the kind of monomap order? You get the sort of opposite thing, where in this tree-like ordering, I've now captured all the entanglement. But in sort of, if I look at it in kind of local order, I don't have the same thing. And you can also ask, well, what's the kind of optimal ordering, right, as a function of this exponent, right? So what ordering kind of captures the structure of entanglement? And so in purple and one, this shows, I think, that the sort of local and tree-like picture are maybe the right ways to think about this, but also at this sort of 0 point, it's not really clear, I think, what's the sort of right geometric picture for how they are interacting. And in particular, that means to some degree that the entanglement as a set of correlations is now like very non-locally spread out, at least from a bipartition standpoint. Okay, so like on this kind of approach, we have, sort of, we want to be a little more concrete about how do you quantify entanglement in these kind of ensemble systems. To what degree do you have control over temperature? Can you, make like a hole in these kind of tree structures? And to what degree, when I make a hole, does it act, as a so we have some ideas, I guess, on this. This is just sort of simulation, but very excited to learn more from. And yeah, so with that, let me just wrap up the sort of global dynamics and local operations. It's a powerful framework, I think, for quantum many-body physics. And we think this is kind of a time-efficient way that extends to sort of discrete qubits and not just these ensemble systems. So right now we're working actually towards using this for enhanced sensing of kind of multiple quadratures, so using this kind of PPR state for enhanced sensing of simultaneously of non-commuting observables. But just generically, we have ideas for sort of on this quantum gravity kind of angle. But you could think more in the future if you have sort of stronger atom cavity coupling, you maybe don't need these ensembles, you can start to generate maybe some of these error correcting codes, cavity codes with kind of direct ties to the sort of interplay between quantum information and quantum gravity. But yeah, I'm here to learn from you. So with that, let me just hit everyone in. Happy to laugh. So the tricky thing, I guess, is that it's four body. So the two body interaction kind of comes in kind of, let's say, a second order perturbation theory. Yeah. So the Sasha Lieu, I think, is more feasible. I think there's some questions about kind of spectral resolution. So I want a random coupling between every pair of sites, then I now need like order n squared different frequencies that I have to like fit into some window. So I think the completely kind of random couplings is challenging on this particular experiment in the near future, but it's like, definitely kind of reality. I don't think it's a fundamental. Yeah, so I think the tricky thing with higher dimension So I mean, I guess we had like some sort of quasi 2D like 3D geometries. I guess experimentally there's some limit, right? So the sort of biggest system that's been measured right now, or the biggest array is like 6,000 atoms, right? So, but I think there's like, let's say a reasonable platform goes 100,000 atoms. But at like higher dimensions, like just the length of my box is just getting smaller. So I think that's kind of the fundamental limitation. This is how many you can track to get to.
The one is that in order to have a weakly coupled gravitational query, the new quantum system has to be very strong and coupled. And from talking to certain experimentalists, it seems to be hard to try. Primarily because you need to continue to a critical point, so you have a very strong interacting query. Is there any, like in the AMO world, are people trying to do that? Are there feasibility outlooks?
Yes. So there's a paper from Conquet and Norman now at Harvard where they use a set of Rydberg atoms in a ring and in a square, like a 2D square, and try to extract sort of universal exponents by tuning to a critical point. So there they find like there's some like decoherence infused kind of exponential decay, but if you like account for that, which you can from sort of single body terms, then you can recover the kind of parallel decay, and that's with a set of effective qubits. So I think there's lots of work.
So am I understanding correctly that basically the adjacency matrix comes from the particular photons you're making you have, is that right?
So the adjacency matrix, I guess I think of as more like this is the target that we want to engineer, and then sort of diagonalizing gives you just the natural basis, where gives you the natural basis for that set of coupling. But it also gives you like sort of a nice set of linear combinations of different ensembles such that you can interact collectively with each ensemble.
So what we have in linear and Hamiltonian is just the photons that we have.
Yes. Yeah, and basically but the photons are always going to be in the same mode. They're going to do the same thing. And so basically the idea is we want to tune which atoms are going to talk